Hello and welcome everyone. I am Servet Bora and today I will present to you our work on solving rearrangement puzzles using path defragmentation in factored state spaces. So let's start. In this paper, we tackle complex rearrangement problems where objects are logically linked to each other. So a few examples are doors, which have to be opened to move an object, or furniture, which must be moved out of the way to exit a room. Here are also two examples from our puzzles. In the first row of the picture, for example, we have a problem where we need to move the green cube that is only movable on the table to the half-transparent green depicted area, and its path is blocked by some rotatable doors. And in that case, the optimal action sequence would be rotating the doors first and then moving the cube in only one single action to the goal position. In the second scenario, a door of a room as seen here in blue can only be opened if it is unlocked or the blocking red object is rotated to some certain degree. In order to solve such problems, we propose a motion planning approach where we can efficiently get the necessary action sequence to solve the problem. To achieve that, we present a new state space that is called the factored state space. So a factored state space is a translation of the movement constraints of the objects into a state space that is divided into logical parts, which we call as factors. As you can also see in the figure, in the problem environments, let's say we have these three objects, and each one is represented by its corresponding factor, here depicted in its color in the state space. And having that, we build an RRT-based planner that we call lowest actions RRT that can efficiently use the benefits of the factored state space and can deliver low action costs. And finally, we manipulate our results with the RoboFlex library in simulation. So to solve the problem using motion planning, we introduced the idea that we can divide the state space into logical parts that are called factors. And these factors represent simultaneously manipulatable portions of the state by a robot. As shown in the figure on the right side, there's a cylinder with 2 degrees of freedom, and a door with 1 degree of freedom, and a prism with 3 degrees of freedom, and each represented by a factor. Having this structure, a movement of an object, let's say the green cylinder here, would correspond to a change only of the green factor's indices between two states. And this capability enables us to plan a path to solve the rearrangement problem. And having the factored state space, we utilize different methods in our planner LART to enhance its planning capabilities. These are, for example, factor interpolates, where we only interpolate along one factor that correspond to the movement of only one object, and a multi-layered cost heuristic to be able to distinguish between the action and the distance cost at the same time. And most importantly, the path defrag method that works like a disk defragmentation, but in our case, it tries to reduce the number of actions a robot has to execute to solve a puzzle. And now let's take a look into our results. Here we can see one of our maze scenarios, the maze 3-door scenario, where the cube needs to be moved again to the half-transparent green area, and its way is blocked by some 3 rotatable doors. And here's the optimal action sequence, as you can also see in the video, rotating the 3 doors first and then moving the cube to the desired goal position. Coming to one of our escape room scenarios, as the name itself says, the robot needs to escape the room where its path is blocked by some obstacles, furnitures, and different objects. The optimal action sequence in that case is moving the 2 red cubes first, then moving the door lock, as shown in red, and then finally opening the room door and driving itself out. Even though we do not provide any optimality guarantees, we are still able to outperform the state-of-the-art planning algorithms in terms of solution cost, that is the number of pick-and-place operations, to solve the problems in this case, in all of our scenarios. And also, it is also worth mentioning that for the maze scenarios, for the table puzzles, we can still be as fast as the best algorithms such as BitStar. And for escape room scenarios, we struggle a bit in runtime due to more dense environments and many more collidable objects in the room and high problem dimensionality. However, only our algorithm still outperforms other algorithms in terms of returning a realistic solution cost. And that will be all. Thank you for listening and see you next time. Bye.